This is the planet 55 Cancri E. This planet has a diamond core. And this is the planet Mercury, smallest and the closest planet to the sun. And this is also made out of diamond! Are you wondering how? Just stick with this video, and I will explain you in just 3 minutes. So welcome back, my friend. This is the Galactic Hub, and today you're going to learn something new. So let's get started. The solar system's tiniest planet may be hiding a big secret. Using data from NASA's Messenger spacecraft, scientists have determined that a 10-mile or 16 kilometers thick diamond mantle may lie beneath the crust of Mercury. Mercury has long puzzled scientists, as it possesses many qualities that aren't common to other solar system planets. These include its very dark surface, remarkably dense core, and the premature end of Mercury's volcanic era. Also among these puzzles are patches of graphite, a type, or allotrope, of carbon on the surface of the innermost planet of the solar system. These patches have led scientists to suggest that in Mercury's early history, the tiny planet had a carbon-rich magma ocean. This ocean would have floated to the surface, creating graphite patches and the dark shaded hue of Mercury's surface. The same process would have also led to the formation of a carbon-rich mantle beneath the surface. The team behind these findings thinks that this mantle isn't graphene, as previously suspected, but is composed of another much more precious allotrope of carbon. The team behind these findings said, "We calculate that, given the new estimate of the pressure at the mantle core boundary, and knowing that Mercury is a carbon-rich planet, the carbon-bearing mineral that would form at the interface between mantle and core is diamond and not graphite." This new study also relates to a major surprise that came a few years ago when scientists re-evaluated the distribution of mass on Mercury, discovering the mantle of this tiny planet is thicker than previously thought. The team investigated this here on Earth by using a large volume press to replicate the pressures and temperatures that exist within the interior of Mercury. They applied incredible amounts of pressure, over 7 gigapascals, to a synthetic silicate, acting as a proxy for the material found in the mantle of Mercury, achieving temperatures of up to 3,150 degrees Fahrenheit. 2,177 degrees Celsius. This allowed them to study how minerals like those that would have been found in Mercury's mantle in its early existence changed under these conditions. They also used computer modeling to assess data about Mercury's interior, which gave them clues to how the diamond mantle of Mercury could have been created. NAMWR, or User Association of Automation Technology in Process Industries, said that when Mercury formed around 4.5 billion years ago, the core of the planet was fully liquid, progressively crystallizing over time. But the liquid core before crystallization contains some carbon. Crystallization, therefore, leads to carbon enrichment in the residual melt. At some point, a solubility threshold is reached, meaning the liquid cannot dissolve more carbon, and diamond forms. And diamond is a dense mineral, but not as dense as metal, meaning that during this process, it would have floated to the top of the core, stopping at the boundary of Mercury's core and its mantle. This would have resulted in the formation of an around 0.62 mile, 1 kilometer thick diamond layer that then continued to grow over time. Mercury formed much closer to the sun, likely from a carbon-rich cloud of dust. As a consequence, Mercury contains less oxygen and more carbon than other planets, which led to the formation of a diamond layer, Namur added. However, Earth's core also contains carbon, and diamond formation in the Earth's core has already been suggested by various researchers. The researcher hopes that this discovery could help reveal clues to some of the other mysteries surrounding the solar system's smallest planet. A major question that I have about Mercury's evolution is why the major phase of volcanism lasted only a few hundred million years, much shorter than other rocky planets. This must mean that the planet cooled down very fast, Namur said. This is partly related to the small size of the planet. But we are now working with physicists to try to understand if a diamond layer could have contributed to very fast heat removal, therefore terminating major volcanism very early. Namur said that the team's next step will be to investigate the thermal effect of a diamond layer at the mantle core boundary. This study could be supported by data from a mission that will follow in the footsteps of Messenger. And your next step should be to watch my other videos for more interesting space facts.